Okay, so how is that?
Then can we do the double derivative
Ooh,
graph?
boy, you're ambitious. That's good. You can. So with the black or with the green or both. It doesn't really. Okay.
Yeah.
So let's say also F double prime. I'm going to take out the blue. We need something else. Okay. So how do you want to do this? This is tough because if you want to look at the original function, then that means you're going to look at concavity and inflection points. But if you want to look at f prime, then that means you could do the same thing, mins and maxes and rise and fall.
Would the shape of the second derivative depend on like what the power number of the original function was as well?
It will, but because you're not given that in the problem, then you can't determine that. That's why
Okay.
both of these green ones would be okay.
So then,
But what we're saying is based on the shape alone, you should be able to figure out a rough graph. Rough.
Could it just be a tangent line for that parabola?
No, what you're going to be doing is to be sketching the graph of the accumulated values of the tangent line. That's where you have to graph. Yeah. So if you look at the green graph, right, the tangent line has a zero slope at what point? Because it's only in one location, the bottom. So it's going to have it here. So basically when x is 0, right, the derivative is 0. So your second derivative has to have an output of 0 at the origin. It has to go through that point. And notice that this blue point coincides with what thing on the black curve? This is a special point.
inflection.
It's an inflection point. So notice it's concave downward here, black curve, concave upward there, and that's what the second derivative tells you. So then back to the green curve, to the left of the blue point, the slope is negative, right? So that means your graph is going to be down here somewhere. And to the right of the blue point, the slope changes to now be positive. So your graph is going to be up here. Now, if this is in fact a parabola, then what kind of graph do you get for the blue graph? Straight line, right? So you see where the blue stuff is here? If I'm going to wing it, it's going to be something like that. That would be F double prime.
Wait, so if you go by the concavity, how do you get that?
Okay, yeah, how do you get that? In other words, it's very busy now, the graph, okay?
Yeah.
So look at the black graph. This is F. That part is concave what? Up. And notice that the blue graph is giving you positive values, so the second derivative is positive.
Okay.
So that's why it's above the x-axis there. And concave downward here.
So you mostly go by the function.
You can go by the function, but actually we did it mostly with the green. You can do it with the green too.
Okay, yeah.
Yeah.
And what's the conceptual meaning of double second derivative?
Well, this one tells you how the curve bends. That's the conceptual meaning. So concavity is, it doesn't tell you about where it's rising and falling. It tells you how the curve is bending. That's
Okay,
good.
so
Yeah.
basically like whatever direction, like the end of that first function, like the normal function f, like
Yeah.
so since it's, you know, increasing on like as it approaches positive infinity and decreasing as it approaches negative infinity, so that always means that that second derivative is going to do the same, or no?
Okay, I see what you're saying. No, there are examples that would contradict that. In other words,
Okay.
that's a good question that you're asking. This could actually bend that way, and so it could be concave upward down here,
Right.
but it's concave
okay,
downward.
okay.
So there's always a counterexample. Right. So the point here is you have to rely, to sketch the green graph, you have to rely on the rise and the fall of the black graph. But to sketch the blue graph, you have to rely on the concavity of the black graph. So you're looking at the very specific derivative and how it's associated with the function. This is hard to teach. I mean, like you just have to do several problems and then it starts to click. When I do this in class, oftentimes someone just says, "Oh," like out loud in class, and then it's like it just worked again. Yeah. All right. So, do you have one you want to ask? All right.
30.
All right.
Specifically, I think D.
Yeah. You can pick it.
Yeah, D.
Okay, so 30. Number 30, part D. Okay, you guys should be super good at this, right? So we're tested on this. How do you go about this one? It's kind of a class. It fits a regular mold of. There is something you could throw at this that would work. Yeah. So let u equal 1 plus x. Okay, and then find the derivative and transform this problem from x's into u's, right? Then work out the details with u, and then come back and answer the question. Right? So the derivative here would be 1. So this means du and dx are the same. So I'll put those in boxes. And then who recognizes there's something here that's not accounted for? It's the x, right? So you could say this is all set and this is all set, but the x right here, you need to get that. But you can get that right from this top equation. That's u minus 1. So all these things that are circled, you can put right into this problem, and you can transform it. Now, something you can do if you want to, I'll go with whatever you guys prefer, is this is a definite integral, so you're going to have to change the limits of integration. But the other thing you could do is to actually solve the entire problem, then bring it back to x's, and then just use 0 and 3. Right? Does anyone care? Nobody cares. You see what I'm saying? There's a difference. Because some people, the one way you could mess this up, right, is you could solve the problem with u and then put in 0 and 3, and that would be wrong. Because u is not 0 and 3, right? This is the lower limit for x, and this is the upper limit for x. So you have to kind of pick one strategy and just go with it. You're going to say something or no?
No, I don't
I
think
can
so.
tell. Right.
So you can solve the whole problem and then put back in the x's and then use the 3 and 0?
Exactly.
Can we do it that way?
That's the way I would do it. There's no point even making a big deal of changing the limits, okay? All right, so basically what we're going to do is this problem. Okay, so you can ignore the 0 and the 3 and just do that problem first. So let's make all these changes here. Okay. So x is u minus 1, this is square root u, and dx and du are the same. So this becomes mostly an algebra problem now, where you can multiply through the square root u, do the integration, and then get your answer. So I'll distribute this. Okay. Notice we're still writing down the integral because we haven't yet done that. So this is u to the 1/2 power. It's going to make that u to the 1.5, right? 3 halves, and minus u to the 1/2. Okay. So now both of these are power ready, right? You can use the power rule on each one. So add 1 to the exponent, divide by the same number. U to the 5 halves. I'll write 2/5. like that. Now you can write plus c if you want to, but you don't have to because this is a definite integral. Okay, so now this is the place where you want to put 1 plus x back in place of u. Okay, so these two are equivalent. And then now we're going to use these, right? The 0 and the 3. So you'll never see this printed in a book, because this isn't equal to that. I mean, I'd get in trouble with math people. But you get the point, right? Because we're having an informal discussion here, right? So 1 plus x goes in here, and now you can go back to the definite integral, the original problem. So the important thing is to understand that these are x bounds. So they have to go into the x function, and then you get your answer. Plug in the 3, plug in the 0, and subtract the 2, and that's it. That's the easy part of the problem. The one place where you can't do this is this, right? That's what I was mentioning before. This would be completely wrong, okay? To actually say, put 3 and 0 in here, because notice it would not be the same as what you have here. Okay, so you won't do that ever.
So if you were to go, if you were to input numbers in that, it would be 1 to 4.
1 to 4.
Okay.
Yeah. So you would say when x is 0, right, you could tell that u would be 1. When x is 3, u is going to be 1 plus 3, 4. So. I probably don't need to finish that, right? Because the fundamental theorem, you guys just get put in 3 and put in 0 and subtract the two numbers. And this is going to correspond to the area underneath the curve. Yes?
Can we do 29G?
Yes, we can. So 29, letter G. This kind of looks familiar, right? Okay.
Oh
No, but it's not the same problem. This,
Yeah,
this
this
is
says,
pretty forgiving. Yeah, the 6 is in there.
Yeah.
So what is the answer to this? Because this, you should be at the point.
Oh,
You
can we
could,
do the one without the 6?
oh,
And yeah,
really?
this one is the natural.
Yeah, let's
Oh.
do it.
Yeah,
I
'cause
get
that's a
this.
natural one.
This is
Well,
natural.
I want
log
to
of-
do,
Yeah, okay, so this one is
Horizontal.
natural log of the bottom. That's it,
Yeah.
right? Because u here on the bottom is x squared plus 6x plus 13. The derivative of this is 2x plus 6. It's perfect fit natural log of the bottom function. Yep. All right.
What rule mixes that?
It's the natural log rule. So it's a more complex version of this. So this is the basic one that we talk about, right? So that if you have 1 over x, the antiderivative is natural log of x. And the way you think about this is the function here and derivative there. It's natural log of the bottom function. This is exactly the same form, right? This is the function, and this is its derivative. So it's the natural log of the bottom function.
Oh.
Yep. Okay, so yeah, as you were mentioning, if this were not here, this would be a much more complex problem, right? You would have to add 6 and subtract 6, and then that way you'd have part of a problem that is simple, this is the one we were doing, and part of the problem that is not so simple. So you would have to do this kind of thing, okay? And what we would do is we would take the 2x plus 6,
Yeah, so we just split it up.
we'd split it, yeah. So we can do the second part if you want, just that second piece.
Yeah,
Is that what you were?
yeah.
Okay. So we can just do the negative 6 over that function.
Yeah.
That's fine. Yep. Okay, so if you had that original problem, you would have the natural log part as part of your answer, and then you would have this leftover extraneous integral, and you would have to work with this one. So you could take out the constant here. And I'll be honest with you, I mean, problems like this in Calc 1, this is the top of the mountain, and these are the hardest problems to work out. So what's the rule that you need to do the integral? It's the inverse tangent rule, right? So the whole point of this one is this integral is short in x. You don't have a function of x upstairs, so you have to use a different rule. The fact that this x is up here actually makes it a simple problem, but without the x it's much more complex. So the idea here is to complete the square on the bottom and to make it look like the sum of two squares. So we're aiming for this here. So you'll find this in your textbook, right? The aim is the arctangent integral. So this is the sum of two squares where you have a number squared plus a function squared, and you have the derivative of the function upstairs. This would be the inverse tangent, right? 1 divided by a arctan u over a plus c. So this is in, if I'm not mistaken, the very last kind of oddball section, 7.1, where in our standard Calc 1, we cover all of these things in Chapter 5. For some weird reason, your yellow book doesn't. Okay, so this is not really a calculus problem. It's mostly an algebra problem, right? You're going to play around with this. So who remembers how to do this? How do you complete the square on that?
6 divided by 2 and square.
Yeah. So 6 divided by 2 is 3, and then you basically square 3 and you get 9. Yeah, it looks like this. But at this point you look at these two and you say they're not the same. Okay, so what we're essentially doing here is taking the number 13 and breaking it into 2. So 9 and 4 will do the job. Okay, so we're just subdividing 13 into 9 plus 4. The reason we're taking the 9 is the 9 is going to work very, very well, right, with completing the square. So we're going to pay attention to this, right, just to look at that. And you guys can figure this out. What's going to go in parentheses there? X plus 3. Okay. So notice 3 times 3 is 9, 3x and 3x is 6x. So everything works out. And then 4 can be written as 2 squared, right? So you can see this is a function squared, and this is a number squared, right? It has exactly this form. It doesn't matter that it's reversed, right? As long as you have a number squared and a function squared, you're all set, okay? So this here should go down here with the minus 6, and then you can finish it. If this looks hard, because it is, right? This is tough. I mean, I'm the first one to tell you. It's very easy to watch someone do this. It's much harder to do it yourself.
In the beginning, how do you know to add and then subtract a 6? That's I feel like you have to be really creative.
You do. But you ask a very good question. So, how do you know, like, where is this 6 coming from?
Because the bottom denominator, you can see that x squared just equals the derivative of 2x.
Okay, you are exactly right. So normally the first way that someone would start this problem is they would say, okay, so if we didn't have this, right? We might let u equal the bottom. And then the derivative here would be, look at this here, it would be 2x plus 6. And then you'd swing over the dx. And then you'd say, ah, shucks, right, we don't have a 6. But then that's exactly the motivation. So what you would do here is you would say, if we had plus 6, this problem would actually be easier. So what you would do is you would add 6, but that would change the problem, so you'd immediately take it away. And then you'd say, this is information I can use to get that, but then you have to deal with the other one with the minus 6. Yep. So it all comes from just like trying different things. And so we're not going to add 8 and subtract 8 because it doesn't really help, mainly because of that 6. And so that's, this is basically it here, right? So u is x plus 3, and a is 2, okay? And then the derivative here, du and dx are the same. So all we're trying to do is match this form. And so the basic formula here, 1 divided by a, inverse tangent of u divided by a. So this one here has a, is a perfect fit. Right, so I'll write the answer down for this one. That was minus 6, okay? And it's going to be 1 over a. 1 over a. And the inverse tangent of x plus 3 over 2. Okay. So if the original problem only had a 2x in it, your answer would consist of this one and also that one with a plus c. So this one would be minus 3 arctangent with that jazz, and then also the natural log. So when I do this problem live in the classroom for calc students, they think it's for shock value, and it's not, because if the problem isn't built just so, then it's going to be a hard problem. And like you said, you have to be creative and innovative to make it work. Because with integration, you only have 10 or 12 rules. And to take any problem to make it fit one of those 10 takes a lot of work, unless it's someone doctors it up and makes it nice. So to make it nice, it would have the 6. To make it unnice, it wouldn't have the 6. That's the difference. Okay, so you grab this and grab that. They don't get harder than that. That's good.
Should we expect like a lot of problems like this?
No, you could probably expect one that would kind of involve either arctan or arc sine, but it's not like you're going to see 5 of those. It doesn't make any
So like to
sense.
7-1 to read that.
You have to review 7-1. Yeah, there's a lot of different techniques in there.
Do you have any tips for like remembering which of like those like trig function and like inverse trig function rules are which? Because like especially with the inverse ones, I feel like they're so similar that like I get them mixed up a lot. So is there like any
You mean
easier...
for like integration or differentiation?
I mean either really, because there's a lot of like something over square root of like something that's similar to the other one.
All right, then let me do something for you.
Can we have like a formula sheet on the test,
You
like a
know,
little cheat
this is
sheet?
an ongoing discussion. See, now I'm at the videotape one. Okay. This is an ongoing discussion in our department.
Yeah.
And if there's someone who says, no, I don't give it to my students, you can't give it to your students. You know what I
Yeah.
mean? Because it tips the field. It's not level anymore.
Yeah.
So until that gets someplace, I can't, because someone else says no.
God,
Right.
yeah. There's so many formulas.
And trust me, there's some places where they're never gonna, they don't even let you use a calculator for anything.
Oh, you have to do
No
all
calculator,
plugging in.
no formula sheet.
Oh my gosh.
Right, nothing. So we're pretty, yeah, we're pretty forgiving that we let you use a calculator, because
Yeah.
there's some places where you get to use them in class for understanding, but then when you take a test, you're naked. It's just
Yeah.
you and your pencil and your brain.
Oh, wow.
Nothing.
Do they give you difficult problems? I
Mhm.
feel like.
Yeah, there are
wow.
usually problems with parameters in there, so they'll have an A in there instead of a 5.
So that's probably all graph related stuff then.
Yes. So, yeah, it's,
Okay.
anyway, the question, your question. All right, so how about if I do something quick for you, and I'll do it quickly. You running? Yeah, anytime you have to go or whatever, feel free. I hope it was helpful.
Yeah.
You know, but, okay.
Thank you.
Yeah. What do I think? So I gather your question is sort of like, what do you do if you forget the derivative of arc sine, and then you don't even know the integral of what thing would give you the arc sine, so all that stuff just goes away? You can very quickly, and I mean this, quickly derive one, and then you would figure out the other one just by connecting the two.
Okay.
So if you take this function, and I'll do this fast, but this was done in class, done in one of the sets of notes, right? So the derivative of sine is cosine, but if you want the arc function, then what you have to do is to switch the y and the x. So you would do this, right there. And so the way that you would find the derivative now, right, for this, is you would do it implicitly, because you don't have the y on one side. So if you differentiate this, you're not liking this? This is the arc sine function, because the x and y roles have been switched. But what I'm going to try to show you in this is you only need to know the derivative of sine, not arc sine, to figure out the derivative of arc sine. And most people would take that. They're like, okay, I'll do that, right? So if you differentiate this now, with respect to x, you get a 1 here, and then as we saw in an earlier problem, sine would give you cosine. And then this is the chain rule, right? You get a y prime out of that. Okay, so this is what the derivative looks like. Y prime is basically the secant function, 1 over cosine. Okay. So this is not what you're going to find printed in the book, but this is where I think this will help you. And this doesn't take that long if you completely forget this stuff, right? So if you look at this equation that's circled, the sine of y, so we're going to treat y like it's an angle measure. So this is where your trig becomes very important, right? So if you look at this and you draw a right triangle, okay, so the sine of y is x. So the sine is going to be opposite over hypotenuse. So the sine of y is x over 1, right? So realize this equation that is circled is represented in that picture. That's right there. Now, once you have 2 sides of a right triangle, you automatically have the third because of whose theorem? Pythagoreans, right? So you can go through and do that. It's going to be 1 squared minus x squared. And that's where you have the aha moment, like, wait a minute, that is familiar, right? So it's going to be under the square root, just like that. Okay? Now, if you now look back up here, where you have the secant of y, you just need to read off the secant function, right? The secant would be hypotenuse over adjacent, right there. So the secant of y would be 1 over this. And that is the derivative of arc sine. Because it started off with the original function, right? Y equals the inverse sine of x, y prime is that thing. So we have this result here. So I understand you wanted more of, you said, can I have a tip?
That's
my
actually
tip.
really helpful.
Yeah.
That's really helpful.
And the only thing here is you only have to know how to differentiate sine. You do have to know implicit differentiation and trig, right? But you just keep on turning it back. But that's the point, is that you get that pretty quickly. And notice what comes with this, is you'll get this for free. Okay, so you get the one going in reverse. It's automatic. And so the same thing works for arc tan.